Okay, my name is Zijian, and I will do the beginning of this lecture as well as some part in the middle. So today's lecture is on training neural networks, and specifically we only covering the first half of it. The part 2 will be next week. So where we are now, okay? So we talk about computational graph in the sense that we can express any function in terms of a computational graph. So you see the graph here, there's data, and then there are some operations inside. So it will show, the computational graph will show how the data flows through the graph and what operations you apply on them. And specifically, we talk about neural networks, which is a type of a computational graph that the computations are more or less the linear layers where we do the linear multiplications. And between the linear layers, we insert the non-linearities, which we call the activation functions. So some of the activation functions that we briefly talk about are like the sigmoid function, the ReLU function. So those functions we didn't really cover much in detail, but we will cover it more in detail today. Then since this is sort of for vision, so last week we talked about convolutional networks, which uses convolutional layers to preserve the spatial structure throughout the hierarchy of the network. So this is how a convolutional layer looks like. So each activation map that you see on the right side, right, is produced by sliding a filter of weights of the input. So for example, this thing here is the filter you want to slide across this input image. So let's say the filter is currently here. We do take a dot product between the filter and the input at this location to produce an element here. So this element is just one number in the activation map. So after we slide the filter across the whole image, right, we get this 28 by 28 by 1 output. So note that the convolutional layer, because of this convolutional property, right, it only has a local receptive field. So this differs from the fully connected networks that are more typical for other purposes. So what I mean by receptive field, right, is that let's say I have a value that changed somewhere here. Yeah, at the top right-hand corner of the image, it won't affect this element because the receptive field is only on the center. So we also learned that if we stack multiple filters per layer, right, each of them will produce a separate activation map. So for example, if we have 6 times of these 5 by 5 filters, the output will be 6 times 28 times 28. So what we want to do now is how to learn the parameters of the neural network. So we want to learn the, so the weights will be, let's say, the weights of the convolutional filter, fully connected networks. So we briefly covered this earlier in the course where we talked about some optimization and some back propagation techniques. Yeah. So what we want to do is we want to get to a point, the weights that produce a low loss. So loss is the cost function we are trying to minimize. So an example of the loss is, let's say, a SVM loss or cross entropy in terms of, in the case of softmax. The process we do it is called gradient descent. And during gradient descent, what we are doing is we take steps in the direction of the negative gradient. Right, the cost will decrease. So the entire process is called a mini batch stochastic gradient descent. So the process goes like this. First, among all the data, we sample a batch of data. So let's say there are like 1 million data points. We sample maybe 100 at a time. Then the second step, we forward prop it through the graph. We do a back propagation to calculate the gradients, and we use these gradients to update the graph. Okay, so for today, we will cover more specifics of the training neural networks. Specifically, we will cover the initialization, which is the one-time setup. We will talk about the activation functions to use. What is the differences between sigmoid, ReLU, this kind of thing. Okay, we will talk about data pre-processing. We will talk about how to initialize the weights. how to do regularization, how to control it, and how to check your gradients to make sure everything is sane. Yeah. Then in the second part, we also talk about the training dynamics, how to babysit the learning process, how to do parameter updates, optimization. And in the third part, it will be evaluation and model ensembles. So for today, we will only cover a subset of those topics. Specifically, we will cover the activation functions, data pre-processing, weight initialization, batch normalization, babysitting the learning processes, and hyperparameter optimization. So Yaqi will talk about the first part on the activation functions. Yeah. You can write using a stylus if you need. The back is the eraser. Yeah.
Okay, next I will talk about the activation functions. Okay, as we saw earlier, there are some inputs. On each layer, there are some inputs, weights, and other bias when we pass function for nonlinear. And here are some examples. Functions. We have saw sigmoid previously, and we have also saw the value last week in CS. So the first activation is sigmoid. So this is the sigmoid function. So it basically just push the input into range 0 to 1 element wise. So if the input is very positive, for example 10, the output will be near 1. And if the input is very negative, then the output will be near 0. If the input is near 0, then it will be a bit like a linear function. So it can be interpreted as a firing, the saturating firing rate of the neuron. And later we will talk about ReLU, which is more biologically possible. Okay, next. If you look at this function more carefully, we will find there are some problems with this function. The saturated neuron Q gradients. So what does this mean? Let's look at the sigmoid gates. We have some input X and the output of the sigmoid function. And during the back propagation, we have the L, the sigma, which is the upstream gradient passing down. Then we multiply it with the sigma, the X, which is our local gradient. Then we chain them together to pass to the downstream network. In this case, what happens when X equals -10? Very negative. Let's look at this graph. And -10, it will be basically just flat. So we will get a near gradient. Then we use a 0 to times the upstream gradient. Then we will pass a near 0 gradient to downstream network. And the same thing happens when X equals 10, very positive. X equals 0 or near 0. Next. And the second problem is sigmoid outputs are not zero centered. Problem. Let's look at this function. We have the input, then we multiply by weights and on W. What is the gradient on W? W is just this local gradient, which is this linear function dW, which is basically X gradient. So since all our X are positive, then since all the X are positive, so it will be a positive number times the upstream gradient. So the output will be all positive or all negative, depends on the sign of the upstream gradient. In this case, this means on the gradient updates can only move in some directions. So this gives very inefficient gradient updates. So let's look at this example. Suppose W is two-dimensional. So in this case, because since all the X are positive, so the gradient on W can either be all positive or negative. So the gradient updates can only be two regions. Our optimal W is this blue arrow. Our gradient updates cannot go along this direction directly. But instead, we need to go through this zigzag path, which is very inefficient. So in general, we want our data to be zero-centered in order to avoid this problem. Okay, the third problem is the explanation function here is a bit computationally expensive. If you look at the whole network, there are all others like convolutions or products, which are more expensive. So it's just a minor issue. Okay, now let's look at the second activation function, NH. As you can see, it's very similar to Sigmoid, but instead it just squash the input into range -1 to 1. So now it's zero-centered, but however, you can will be similar actually. Similar.
Okay.
So it's just a variation of Sigmoid in my understanding. But it still kills gradient when it's saturated, so it's a bit better than Sigmoid, but still have some problems. Look at ReLU. So ReLU is this. It just takes the maximum between 0 and the input element vastly. And if you look at this function and think about the problems we saw earlier in Sigmoid, we'll find that it does not saturate in the positive region, and it's very computationally efficient since it just takes the maximum. And in practice, it converges much faster than the Sigmoid function, around 6 times faster. It is more biologically possible found by the neuroscience experiments. However, there are still some problems with it. The output is still not zero-centered, and in the negative region, it gets saturated. So the same thing happens. When x equals -10, very negative. Basically, pass the zero gradient to the downstream when x is smaller than 0.
Do you know why it's considered more biologically plausible? I mean, Serena says that it is, but she didn't cite any.
I feel like it's just measured by the neuroscience experiments, and they put some electrical plates on the human's brain. Then they measure the electricity waves of the human brain, and they feel like it's more like ReLU.
Citation for that.
If I can give it a try, if you go back to the graph over there. So, like in a biological neuron, it either like fires or it doesn't fire. So in this case, it would be completely fire or it doesn't fire at all, as opposed to the other graph, which if you see split up as intermediate states, which doesn't exist in a typical neuron. Because either you fire or you don't fire. There's no halfway point. That's my guess.
But this ReLU, right? The strength can go as high as possible. So, but if you use does that mean that in a neuron, the electrical strength that come out is not kept to a certain range?
There is a cap.
We basically mean the differentiation at that point.
Yeah.
So at all these places, it's going to be constant. Differentiation becomes a constant value. Here, it's going to be 0. So something like that.
So I remember Serena saying it's related to the firing rate in the video. So meaning that when a neuron fires, it fires, but it fires repeatedly. And the stronger the signal is, the more times it will fire per unit time. So I think that's what is meant by this slope, is to say that the higher slope, that means the neuron is constantly firing more and more active, rather than the strength of the electrical impulse that's going out. But I still don't have a very good intuition why she would say that's biologically inspired. So I was wondering whether anyone was able to find any direct evidence of what Serena said in her lecture.
So just proceed. Okay, so So according to the problem we just mentioned, we will pass a zero gradient to the downstream network if the data input is less than 0. So we can get that. This is our data plot, which is our entire training set. And these two lines represent the resulting hyperplane of the input times the weights. And these arrows will represent the value they are dead. So it's still an active research topic, but in practice it still works even with some dead values. Okay. And in practice, people like to initialize the value with some positive bias. So this is just to increase the likelihood of being active at the initialization state to get some updates. So you can see it just biases towards the positive thing. So in practice, some people say it works, but some says it doesn't.
In the value, since that means that regardless of the input data, right? So it means that it's pointless to compute those, right? Because then does it mean that if we can find out which units are always dead, then we can save some. I mean, can we do that? I mean, can we save some computation by determining?
Alluding to dropout, right? The case where, yeah, because in dropout you will test like the different layers and then see which combinations maybe are not as important in your overall prediction.
But dropout is not applied during testing, right? It's only applied during training. So, but this one is, I know that like for the certain range of value units, they are always 0. So I know somehow, okay, but because there's an estimate, right? Like 20%, so they must have a way to figure out which one are dead. Then I put a mark, something that says that, okay, these are dead values. So I don't want to compute that anymore because, give 0 anyway.
I guess, but yeah.
I guess the computations happen matrix wise, so you can't do anything with that.
Yes.
I see.
I feel it's more costly if you separate.
Okay.
So we had this discussion last week about how the GPU does the computations, right? So this thing, but it's also related to the earlier point about dropout. So dropout is when we specifically train in a fashion to drop neurons. And I guess next in week 6. That's part of how you're training. It's a zero gradient, and then suddenly that part of the network is dead. Right? It's no longer functioning. Even if you want to backcrop through, there's nothing to propagate because it's not getting anymore. And so Zalman's point about saving computation would probably make sense in this CPU-oriented fashion, but maybe for GPU it doesn't. That's my take on it.
So let's look at some variations of the value. The first example is the leaky value. You can see it's very similar to value, but instead of being just flat in the negative region, we have some small slope. So this actually solves a lot of problems. So it does not saturate on both planes, and is still computationally efficient, still converges faster. And most importantly, it will not die. And the second example is the P value. It's also very similar to the decay value, but the slope is controlled by alpha parameter. We don't need all the benefits of the value, and it has a close to zero mean output, almost no absolute zero. And if we compare it with the T value, we'll find that actually we are building back some saturation in this negative plane. So this gives us some robustness against the noise due to this deactivation states. It's a bit more computationally expensive since it has exponential function here. And next one is Maxwell neuron. This is a bit different. So it's just taking a maximum of these two linear functions. So it generalizes the value and the decay value. As a linear region, it does not saturate and does not die. The problem is that it doubles the number of parameters. You can see there are two weights and two biases here. So in practice, the general rule is to use ReLU because this is the most standard one, but be careful with your learning rate. You can also try out Leaky ReLU, Maxwell, and eReLU. You can also try out 10H, but don't expect much. And don't use CMOS. This is one of the earliest original activation functions. Other activation functions like ReLU and its variants works better than it. Of the activation function. Next, we will proceed to data preprocessing.
Yeah. Hello everyone, my name is Hugh, and I will present about preprocess your input data and initialize the weight for your neural network. So to preprocess your data, usually first you will because there's a problem with your data is not zero-centered as presented before. So first thing to do is to shift the data to make it zero-centered. And one way to do that is to subtract it with the mean value of the data. Approach to preprocess the data is to normalize the data. Because if the data has many features and the features don't have the comparable scale, so it will be a problem. For example, rate for the weight of the features will be different. And sometimes the neural network will tend to learn more about the features that have a larger scale. Yeah, and so this is the problem with if your input data is not zero-centered. And there's other approaches to normalize the data, such as BCA and whitening. Details about these approaches, because usually for neural network for computer vision data at all, because usually the input data is bit cells, 3 dimensions, red, green, blue, and they are of same scale, so there's no need to data at all. To subtract To make the data zero-centered, there are two ways, common ways. The first one is to calculate the mean image among all the images in the training set and subtract it with all the images. The second approach is to calculate the channel, for example, red, green, blue. Thing to note about preprocessing the data is that the statistic you use to preprocess the data have to be derived from the training data, not the testing data. For example, when you subtract the input data with the mean have to be calculated as the mean of the training data. Calculate the mean of the test data here. Yeah.
I have a question because I was trying to find some references on the difference between these. Are they exactly the same? I mean, in terms of the final performance, if I use the whole mean image versus I use per channel mean, better, or they are about the same? Because if they are about the same, then we should prefer the per channel mean, right? Because it's a lot more convenient.
Yeah.
Is there a difference in terms of performance?
Okay, this one I'm just guessing, but I believe that there's no definitely better or definitely worse scheme for all scenarios. So usually what we do is we will try both and then just pick the one that works better during cross validation. Yeah. And anyway, it's because this subtracting the mean or subtracting the per channel mean isn't done like as you train. I mean, it's only done only at the data at the start. So actually, it doesn't really introduce much computational complexity also. So
okay, but having only 3 numbers versus a mean image to the right, I mean, it's a lot more convenient, right? So,
yes.
Yeah. Because recently, I think the recent architectures like ResNet, GoogleNet, they no longer do the first one, right? They only do the second one. So, but I was wondering whether is it based on some hard performance numbers, or it's just okay, the first one is too troublesome, let's just do the second one.
So it really depends on the data set that you're working with. Your data set contains a lot of, let's say, like darker images or redder images, then probably, the second one is going to make a lot more sense because then it's like all of your variables are going to be centered around around 0 with a mean of 1. But if you're dealing with like a regular neural data set, like for example the InitialNet challenges, then it probably should be okay for you to use the first one where you just subtract the mean images because like there's such a large variety of images. However, it's like your data set is skewed or is just a small sample of a subset of data, then probably you want to go with the second option. But in any case, like it shouldn't make too much of a difference because you know, most of it also depends a lot more on your optimization formula. If you're using something like Adam with learning rate changes as you introduce more and more batches, then the centering about the mean and centering about the mean per channel, it wouldn't make too much of a difference. Rather than, let's say, other factors like hyperparameter tuning of each of the nodes.
But so from your argument, it seems that the ImageNet is becomes sort of equivalent to the second one because it has the average is out to a single approximate number for every pixel. So so if the data is biased, it means that if we use the first approach, there will be some spatial biases introduced, so that we should not prefer because you are basically introducing spatial biases in the data.
Right.
I see.
I guess so. So maybe the second option might be a better general approach rather than the first.
Okay. Got it.
Second one, you're assuming like there's translation and variables, right?
Yeah.
Do the second. So every part of the image is like the same. Treating the same.
Yeah.
You don't care about where each pixel.
First one, you have some biases introduced. Like, okay, maybe if it is a cat, the cat might. Maybe the cat usually is on the upper part of the image. Then there'll be more cat-like things on the upper part of the main image, and then yeah.
So now go to normalization for the neural network. So our first guess is to initialize on the weight as 0. But there's a problem if you initialize on the weight as 0. The first problem is that the output of the first few layers will be like approximately and the output of the first few layers will be the input of the upcoming layers, and because the propagation, the gradient will flow upstream down, and because the local gradient at a neuron is like approximately 0 at that point, because the input of that neuron is 0. So basically the neuron is like not, yeah. And if on the initialized weights are the same, so it's like there's a lack of the neural network to be symmetric, like because the many neurons are connected similarly, so basically they will have the similar input, behave similarly, and they update similarly. So they will be stuck at a local minimum. Yeah. So our first idea is to initialize the weights as random numbers with following the Gaussian distribution. Eliminate the problem of having a symmetric initialized neural networks. However, it still remains that the other problem still remains that the output of the first few layers will be very small, approximately 0, because the initialized weight is too small. So let's look at some example. Here's a 10-layer network with 500 neurons on each layer, and they are using tank an activation function. See the first layer, there is no problem with the first layer, but for the other layers, deviation of the data is approaching 0 because the incoming data of that is really small. Yeah, so basically that's what I just talk about when the input data of the layers at the back is very small. So our next case is to, instead of multiplying it with some small number like 0.01, we multiply it with a larger number such as 1. So if you look at the graphs here, so it means there's some problem with it. So what is the problem? The problem is that if the initialized weight is too large, then because we are using 10H at the activation function, or someone will use liquid review, for example, is too large, so the output of the neuron will be large. You go to the extreme of the function, like the 10H, you go to the extreme of the function, and basically the gradient at the point is nearly 0. So it like the neuron there is saturated from the beginning. Yeah.
If you can you please summarize the previous graphs again, why we shouldn't initialize it with small numbers?
I'm sorry.
few slides you talked about why you shouldn't initialize it with small numbers. Initialize W with small numbers, right?
If the initialized weight is too small, then because the output of a neuron will be input of another neuron, so the input of other neuron will be very small.
Oh, okay.
So he's like, initialization is like, we involve some mathematics proof here. We won't go into details into it, but the purpose of it is to guarantee the variance of the distribution of the input data is similar to the variance of the output data of each neuron. So basically, the more input data of a neuron that it has, the smaller the variance of the initialized weight that neurons will possess. That's why in the equation right here, we see the weight will be something divided by the number of inputs, because it will be disproportionate to the number of inputs. Yeah. But if we use the same formula for the some other activation function, such as ReLU, it will not work. For example, for the ReLU activation function of the neural network, half of the it's like
more like because the negative vision is all set to zero. So
yeah, so basically for the ReLU activation function, like before, like the half of them will be like 0, so they will not be fight at all. So we will lose these half them. What they suggest is to add the additional divided by 2 in the equation to maintain that the rest of the output is guaranteed, is the same. Yeah, and so proper initialization is still an active area of research.
What is the initial variances? What are those variances of? Is it of the weights or is it of the outputs or the inputs?
Can you repeat the question?
Yeah, what are the variances that you calculate at each layer? Is it variances of the weights, of the inputs, or the outputs?
These variance of the output data.
Variance of the output.
Yeah.
Okay.
Yeah.
Okay, I'll cover the part on batch normalization. So just now in Hugh's part, we talked about the fact that we want to keep the activations between the layers, right? Something like a unique Gaussian small, otherwise the gradients will die off, or we don't want it to explode. So batch normalization plays about the same idea. So which is that we want to keep the activations in the Gaussian range. Okay, the idea of batch normalization is that we want unique Gaussians, right? So why not just make them explicitly that way? So how does this work? Consider a batch of activations at some layer. So we run through the stochastic gradient descent, we pump through a batch of data, and we get some activations. So if we want everything to have a unique Gaussian, so meaning the mean is around 0 and the standard deviation is around 1. So what can we do? So actually we can just do this empirically, right? Okay, we can just take the mean of the current batch, subtract it, the sample variance. So instead of the previous section where we did the weight initialization, do data pre-processing, so where we set the weights at the start of the training and try to get everything in a good spot. Hopefully everything, all the variances of the activations, right, will remain roughly at 1, right? Why not? So what we are doing in batch normalization is we are forcing the activations to have a shape. So we are making this happen explicitly. So one thing to note is that taking this mean and variance, right, and subtracting it away, right, is just a differentiable function. So we can just compute the mean and variance, treat it as constants, and do the minus and subtraction, and it can be easily computed and differentiated. So to illustrate how batch normalization works again, right? So let's say we have the input data, we have n of them, and each one has d dimensions. So this n corresponds to the n samples in the current batch. So what we do is we compute the empirical mean and variance independently for each dimension. It's not a covariance or anything, it's just a simple per dimensional variance. Then we normalize the activation. So it's quite cheap to compute, yeah. And we insert these batch normalization layers, right, regularly in the so mainly we usually insert it after the fully connected or convolutional networks and between them and the non-linear layers. So meaning we insert it right after the fully connected network and before the 10H in this example. Yeah.
Why not after 10H?
Later, maybe I hope I'll answer your questions in the next slide.
Okay.
Yeah. Okay. So yeah. So this is actually this is related to your question. So the problem is that actually we minus away the mean and divide by the variance, we get a standard kind of Gaussian shape for the activations, right? But is that something we always want, right? Okay. So sorry. Yeah. So actually, if we have let's say a standard deviation of 1, right? What we are doing if we are feeding it into a 10H layer is we are restricting all the activations, right, to only work on the linear part of the 10H function. Because if you remember the 10H shape, right, is actually like S shape, which are two extreme from 0, right, will have a gradient of 0. Yeah. So if we are restraining the input so that the activations is like a standard deviation of 1, right, more or less we are not touching the flatter parts of the 10H. The reason why we have activation functions is because we need the non-linearity. So if we are restricting it to this, right, then we won't get the non-linear part of the activation function. Yeah. So this is why solution for this, right, is we allow the batch normalization to happen, but then another 2 parameters called gamma and beta that shifts the batch normalized activations, right, if they need to. So the gamma will squash or activations and the beta will shift it. Yeah. So note that in this case, right, the gamma and the beta, right, can be learned, right, to recover the identity mapping. So if the network deems that the batch normalization is not useful, right, it can always learn that gamma can be variance of the data and then beta is the expected mean of the data. So you can just remove that away.
But just now the argument only
Yes.
up to 10H, right? What if?
Yeah. So if you use ReLU, right, you also need also a shifting, right? Because you want to control where your saturation point is. Because less than 0 is more than 0 is X. So this is a bit like training your bias and as a spreading of the points. Because even if you ReLU, right, the positive part is X, right? You can make it 2X, you can make it 4X, right? It will matter, right? Yeah.
Okay.
Yeah.
Just use ReLU and your input are all positive, then it's just linear only. You won't touch this.
Yes.
Part.
Control where the
yeah.
Okay.
Yes. Okay, so to summarize the batch norm process, so for each batch, yes, sorry.
In the last slide,
yes.
there's another neuron in another layer.
So the question is whether the beta and the gamma are another neuron, right?
How do we exactly
Yeah. So actually, these are just additional weights for the batch norm layer. So the batch normalization actually doesn't really have much trainable parameters other than these two. The mean and the variance, right, are actually treated as constants. So you have input activations, right? You compute the mean and variance. So those are treated as constants that pass in. So those are not parameters to be trained. So these two are the parameters that you perform gradient descent on.
What is the structure inside the network of the batch normalization? How do we exactly implement
so this one I think I can answer. This is I think it depends on the framework that you're using. Like for instance, in Cafe, it is actually implemented as a scale. So the first gamma is a scaling layer. So B is, I don't know how B is implemented, but it's also, I think the scale layer had a bias. Basically, is another layer called scale, which lands
basically every neuron is just connected to the neuron on top with just one connection or something like that.
Yes, yeah. And also because so this structure, right? In fact, usually this comes after. Right? So it turns out that scaling and shifting can be analytically applied to the complex layer. So because so you are shifting it, but then you don't really have to do it. You don't really have to compute it. Take the scale and apply it to the comp filter, and then you can take the bias and also apply it to the comp biases to have the exact same result. So basically, you can completely remove this portion, and then you can get quite a bit of performance, about 20% improvement. Okay, so you merge it into the comp layer.
Okay.
Yeah.
Thanks. Yes. Yeah.
These means and variances, right?
Yes.
I mean, I understand you can compute them for the inputs, obviously, but you know the deeper layers, right? These means and variances are going to change, right?
Yes.
Then because your weights are changing as you train your network.
Yes.
So do you keep? How do you do that?
No.
Are you using the same?
No, so every time you do a stochastic gradient descent, every time you have a batch comes in, right? So every layer that you insert this batch norm, right, you need to compute the mean and the variance. Yes, yes, but that's during training. During testing, we'll do it slightly differently, which you will see later. Yeah. Okay, so to illustrate the batch normalization process again, right? So for each batch that comes in, right, we first compute the mini batch mean and variance, like what I said just now. Then we normalize all the activations by the mean and the variance, and scale and shift by the gamma and beta. So batch normalization, according to the authors, they mentioned that it improves gradient flow through the network. It's also more robust and works for a larger range of learning rates. So ends up it allows you to train faster. And one more thing is that even though it's not very obvious, right, the batch normalization also acts as a form of regularization in a funny way. So why this works is that when we do batch normalization, right, remember that we compute the mean and the variance on these activations, right? So each time the activations is computed on a different batch of data. So the mean and the variance that we compute, right, will jitter slightly. So it won't be the same all the time. Network has to learn to generalize so that it doesn't, so each input data now, the input activations doesn't just rely on the current input data. It also relies on, it also depends on the other input data that come in on the same batch. So the network will have to learn to generalize across slightly different means and variances. So end up, right, it can work as some sort of regularization, yes. Okay, so during test time, right, we don't do the mean and variance computation. So what we do, right, is we make use of whatever mean and variances that we computed during training. These mean and variances can be, for example, computed using running averages. Because we are doing stochastic gradient descent with many batches, so we want to do some average of the mean and variances that are computed. So any more questions? Okay, Yeah.
question.
Yes.
Why don't we just remove the normalization layer and use the scaling layer because it's also normalizing? Then you can learn its variant, learn the scale factor and
But scaling layer doesn't ensure unique Gaussian.
What?
The reason we're doing this is because we want it to be unique Gaussian. If you use scaling,
you already make it the unique Gaussian. Then after you let the scale layer ununique Gaussian thing. Skip the step and just let the scale layer.
I imagine that the scaling layer is a small shifting. Yeah, it's a small tweak. I mean, for instance, your data is so skewed that initially your data is so skewed that you can never make it unique Gaussian using scaling and shifting. Then you require that formula to do that, to make it unique Gaussian, and you tweak it a little bit using the second step.
Well, I think you have a good point. Why don't you just start with this your normalization, and then that's your initial, the second normalization that you do, right? Why don't you just start with that with the mean and variance, and then you let it. So those are the and then you let it learn. Yeah. So you can skip the entire computation.
Initialization.
But because it keeps changing, it's not the same. Because as you update your weights, your unique Gaussian, the means and variances keep changing. You cannot just do it once because next time you update, it changes already.
Sure, but that's why you can. That's why the parameters, they are like weights. They can change too. So you just initialize them to the first batch. The first batch, the initial parameters for your that correction, the second correction that you do, right?
Okay, actually, I would think that the batch normalization step itself, right, as in the minusing the mean and variance, is still necessary because even if you initialize it right at the start, right, when you are learning, right, especially at the start when your learning rate can be faster, right, once if you update the weights of the preceding layers, whatever normalization you think you are doing may not be valid for the new earlier layer weights anymore, right? So what we are doing when we are forcing it to be unique Gaussian, right, is that whatever happens at the start, right, it will still end up to be a unique Gaussian activation to scale it and shift it.
I think there are probably merits to both. Like you want to do the initialization, normalization to make the whole input nice, but in algorithm you have each layer, right? In each layer you want to treat it as a separate problem to normalize. So it makes sense to do some normalization per layer. But also because it's batch, because you don't want to go through the entire calculation of the entire gradient, you're only doing it per batch. So because the batch is selected stochastically, you probably want to normalize just for that particular batch, right? Rather against the whole data set that you would do on the first pass.
But I think even if you have the time to actually pre-compute all the mean and variances for the entire training set for every layer, you still wouldn't want to do that because, so this is assuming a fixed weight, right? Your weight has changed after an update. So the mean and variances will no longer be the same. So you need to update them as it goes on.
You're making an argument for why it's dynamic, right?
Yes. Yeah. So the stochastic, doing it per batch way is a kind of a cheap way to approximate sure that it's always unique Gaussian. So don't want to spend time computing it, for every layer for the whole training set. So you just use running average to approximate it. Yeah.
Okay. Okay, then Jishnu will cover the last part on babysitting the learning process.
Yeah, so up to now it's basically setting up the network, and this part is you can see like the first steps of when you start training and observing that and fine-tuning a network along the way. So to kind of go over stuff which was just gone over, the first step is to pre-process the data. So that's zero centering by the mean and dividing by the standard deviation. With images, for the first pre-process, you probably don't do this. And So you start with an example architecture, like pretty much as simple as you can start just to do sanity checks. Start with one hidden layer, so 2 layers and 50. That's just no particular reason. And the first step is to just run it without training and or and 2.3. Checking that it's reasonable, what they mean is that you know that the loss function you're using is softmax. So you have this expectation of if you're making a random, like it's a 10 class problem. So if you're randomly picking one class, then your loss is basically you're getting a negative log of 1/10, which is 2.3 by ensure that you're getting a reasonable loss on your first pass through. So this just makes sure that your initial setup is correct. Next step is to just add regularization and see that you do worse. So this ensures that like regularization is penalizing your model and working the way that you expect it to. So then when you start training, the recommendation is to, for a very small portion of the data, again, first, and the test is and don't use like more complex optimizers. Start with simple stochastic gradient descent and either try to get your loss to 0 or whatever your baseline loss is, or I guess your accuracy to 1. So in the lecture when they run, they show that the loss is still slightly not, which basically made your network we start so you start with like the lowest learning rate that you would expect, I guess. The so a max function, so it's very sensitive to even, so you can get like a big result even without having loss function. So you've updated your probabilities enough to do well on some training set, not actually learned much. Yeah, that's. This is pointing out that you're doing a max of at the end. So you said that the learning rate of 10 to the power -6 is too low. Now the attempt is to find an upper bound. So they tried 10 to the power 6 as a learning rate, and what you're looking for now is a loss explosion. That's when you get your training rate is too high. So this will be characterized by like divide by 0 errors, see like NAN costs, or it could be like very high costs as well, or like fiercely oscillating costs.
What does it mean to have not a number as a cost?
So
how's that derived?
Over here, it's because of a divide by 0. So
I suspect that because when you're doing softmax, right, the cross entropy term is actually
P times log P is the data label, the ground truth. So the P times the log P, right? The second P is the white of it. So when your learning rate explodes, right, then it is too large, right? Then effectively the activations will be a large number. So that means you take an exponential and then you divide by the whatever, right? Then so when you take the log of something that is very, very near zero, right, then it can go to infinity. Yeah, taking the then.
Okay. Is the underflow and overflow too high in activation?
Yes. Yeah, so I guess on the learning rate then is just an empirical test to find your rough bounds for what is reasonable, where your cost is not exploding and it's reduced. It's 10 to the power -3 to 10 to the power -5 as their range. And so yeah, for the more particular or rigorous, there's again two stages, where one's a more coarse one and one's a more fine one. So you have a tighter range and you have a box. So you might need to iterate depending on whether you're happy with the results of your second stage. Yeah, and this is again an empirical tip where if your cost is ever 3 times the original cost, you should probably step out of your second stage and at least go back to the first stage, if not even before that. Empirical trick that they point out is to optimize in log space, which means that here the updates are basically in orders of magnitude because they're exponentiating, right? So like you only see noticeable differences in your when you change stuff by an order of magnitude, because a lot of the operations that you're doing are multiplicative. If a unit difference is not much, but like a power 10 difference is significant. So here, basically, this is the range of, they're optimizing for 2 hyperparameters, regularization and learning rate. And it's basically, you can think of it as like a for loop, or at least I think of it like a for loop over those two. And you're seeing at like the range where it does well. So here they've identified that for learning rate in the 10 to the power -4 range, so they point out that this result is worrying, and this is because it is achieved at the rate of learning rate of the 10 to the power -4 and regularization of 10 to the power -3. And worrying because basically you're optimizing over like 2 parameters, so you can think of it as like a 2x2 grid. And this best result is in like one particular corner. It's like the extreme values of your range for each parameter, which means that if you think of it like convex-ish space, ideally when you do this, is grid search. Techniques for optimization. So grid search is the more maybe intuitive, where you have two sets of parameter. You pick, like you have a step size, and you pick each combination of. So if it's A and B and 1 2 3 1 2 3, this is like 1 1 2 1 1 2 1 3 2 2 1 2 2 2 3 and so on. So you're picking well-defined combinations. In random, you basically pick each parameter randomly along each parameter's possible range, and the recommendation is to prefer random search, because these graphs represent like the true effectiveness of the parameters in some way, which is kind of hidden to you when you're doing this optimization, right? You're trying to discover the nature of this function, and it's high. Right. And one of the parameters is unimportant and one is important, but that's not known to you a priori. So if you do grid search, you're exposed to 3 points on this parameter and 3 points on this parameter. While if you do a random search, you get exposed to on this parameter as well as 9 different points on this parameter. So if one parameter, like if the results are more sensitive to one parameter, you can actually see differences along that. So prefer doing random search. Yeah, you're basically doing like a search over these two hyperparameter spaces, right? Yeah, so I mean, in the lecture they go through regularization and learning rate, but there's a bunch of things, right? And it's so network architecture itself can be a hyperparameter, and if I'm not wrong, that's how a lot of like AutoML and neural networks, building neural networks stuff. And a lot of it. Right. So basically, the loss curve is versus the epochs that you train, and you want like a good learning rate. Learning like too low, then you might not reach like. Like at a later stage in epochs, again, which is determined empirically, right? Like in this graph, they have 100 epochs. So I think that is dependent on the problem domain you're in, like how many epochs you train on. Right. So this is basically an example that they point out where the loss function